Hello, today I'm presenting you the work A Flow-Informed Strategy for Ballistic Capture Orbit Generation, co-authored by Professor Francesco Toputo, and recently submitted at the Celestial Mechanics and Dynamical Astronomy Journal. As usual, I will start giving you the context and motivations of the work. After that, I will present you the modeling of the astrodynamics problem we're dealing with, the N-body problem with perturbations. And then I will introduce the ballistic capture phenomenon. I will introduce the definition, followed by a number of objects associated to it, and the limitations of the current approach. Then I will go back to the variational equations, introduce the theory of Lagrangian Coherent Structures that will inform the introduction of a new object that we call stroboscopic strainlines that will be used in the context of ballistic capture trajectory design. Then I will tell you something about implementation and most importantly show you the results of this methodology. And finally, I will give you the conclusions and recommendations for future work. So in general terms, mission design is a trade-off between model accuracy and design feasibility. This can be understood by thinking about the two-body problem and the way in which optimal trajectories, such as the Ullmann transfer, are computed in an easy and straightforward manner. This is not the case when dealing with more complex dynamics. And it's in such a context that low-energy transfers arise. In fact, they leverage dynamical nuances of the solar system, of the dynamical system, describing the motion of the object, and allow the reduction of the delta V associated to the transfer. A subset of low-energy transfers are ballistic capture trajectories, which will be defined more strictly later. And these trajectories are interesting for a number of reasons. First of all, as any low-energy transfer trajectory, they require less fuel compared to traditional approaches. Moreover, they eliminate potential single-point failures. And finally, they widen the launch window. In fact, the target body and the Earth are not necessarily aligned at the launch epoch in order for the trajectory to be feasible. So in this context, Lagrangian Coherent Structures have been introduced as an attempt to generalize the concept of invariant manifold, which separate regions of the phase space associated to qualitatively different behaviors. Of course, we all know that invariant manifolds have been successfully applied in mission design, but these structures exist only in problems which are time independent and that have equilibria from which this structure arise. In more complex dynamics, such as the N-body problem, invariant manifolds don't exist, but we're still interested in characterizing qualitatively the phase space, the motion of the problem, and so we make use of the theory of Lagrangian coherent structures. So this work is motivated by the fact that the computational cost to generate ballistic capture orbits is high. Moreover, an analytical description of the weak stability boundary, an object that will be introduced later on, is still missing. And finally, as said, Lagrangian coherent structures have been recently successfully applied to mission design, and so we're interested in leveraging this relatively new tool to deal with the ballistic capture problem. So the dynamics is given in this slide. You can see that we're dealing with a perturbed N-body problem, which we add to the presence of N gravitational attractors, also solar radiation pressure and non-spherical gravity. And you can detect all the terms in the equation in which the gravitational attraction of the Sun and of the target body are separated from the perturbations of the N-2 additional bodies. And it's important to state that this is the most general framework in which we're defining the ballistic capture problem. We can nevertheless simplify these dynamics and go back, for example, to the elliptic restricted T-body problem, simplifying the trajectory of the target body and removing all the perturbations, or even a circular restricted T-body problem, and look at how the proposed technique that will be based on the so-called stroboscopic strainline can be applied to different fidelities, different model fidelities. So more in particular, here are the formalization of the perturbations. The solar radiation pressure is modeled with the cannon ball model, in which the force is aligned with the Sun, is a central force. It's aligned with the Sun spacecraft vector, and is proportional to a number of constants. Moreover, the non-spherical gravity is expressed using the usual formulation with spherical harmonics and Legendre functions, and you can see the expression here. And we are modeling the non-spherical gravity only of the target body. So this is the modeling of the dynamical system. Now let's talk a bit about what ballistic capture is. Ballistic capture is a phenomenon by means of which a spacecraft approaches a target celestial body and starts revolving around it only by means of interactions with two or more celestial bodies. So we're not performing any maneuver during the approach phase towards the target body. We're just leveraging the structure of the phase space associated to the presence of more than one gravitational attractor to start orbiting a given celestial body. You can see in the figure a sketch categorizing different initial conditions, which can be said to be stable or unstable with respect to the target body P2, depending on the behavior of the resulting orbit associated to such initial condition. It turns out that we can divide the set of initial conditions into four sets: the n weakly stable set, the n unstable set, the n crash test set, and the n acrobatic set. The weakly stable, as the name says, is made of trajectories that perform n revolutions, so it's stable in the sense that it's revolving the target body. The unstable one performs n-1 revolutions, then escapes the target body. The crash set performs n-1 revolutions, then crashes on the target body, and the acrobatic set doesn't behave like all the aforementioned sets. So from this categorization, we can introduce the capture set, which is the intersection of the -1 unstable set and the n stable set. In this way, we can identify the initial conditions that, after being captured by the target body, so they're coming from outside the sphere of influence, let's say, of the target body. After being captured, they revolve n times around the target body. In order to perform this categorization in three-dimensional space, it's not enough to look at the sketch in the previous slide, but we need to introduce a initial condition-dependent semiplane, which can be used then to assess the behavior of the trajectory with respect to it, with respect to space, and therefore assess the stability or different behavior of the trajectory. An important object to be introduced is the weak stability boundary, which identifies the separatrix between those points in the phase space leading to capture orbits and those leading to different behaviors, such as escape orbits. So we have this set of capture orbits, of initial conditions associated to capture orbits. The boundary of this set is the weak stability boundary, and it's strongly characterized by chaotic behavior, because we are just in between escape and capture. And that's the object we're interested in. So to investigate it, we go back to the variational equations. We don't discuss them here, but we introduce the state transition matrix defined in equation 5. And from it, we can introduce the so-called finite time Cauchy-Green strain tensor, which is simply a positive definite matrix associated to the state transition matrix, which assesses the behavior of the infinitesimal value around the initial condition, and in particular defines the stretching of such volume, and can be used to assess chaos, of course, because the more a region of the phase space is chaotic, the more this volume is deformed by the flow. So to make use of this Cauchy-Green strain tensor, we first introduce finite iteration Lyapunov exponents, which is a scalar field that can be used to, again, assess chaos in some way. The details are on the paper, but here it's enough to state that they make use of a particular Poincare section and can be used to assess chaos. From it, we introduce what we call time-varying finite time Lyapunov exponent, in which we have this scalar field associated to the Cauchy-Green strain tensor, which is in some way normalized, but in which we are taking into account the fact that we are considering different integration times for different initial conditions. In particular, starting from the idea of the Poincare section, we can integrate for a time that is associated to the intersection of a section of the phase space a number of intersections in general, n intersections. And it's of course a function of the initial state. Then we can take an additional step and consider as a final integration time the time it takes for the orbit to intersect a physical two-dimensional plane, defined again by the initial condition of the orbit. And you can see that we're going towards the definition of the ballistic capture phenomenon, the three-dimensional characterization of the motion, and introduce a quantification of chaos associated to the definition of the ballistic capture phenomenon. We are nevertheless not interested in this work to identify the behavior of the time-varying finite-time Lyapunov exponent for the n-body problem, even though that would give some information associated to what we're looking into. But we are using this idea to create a new object. And to introduce it, we start from the traditional strainline, which is a two-dimensional, a Lagrangian Coherent Structure defined in two-dimensional space. And one of the conditions for an object to be a Lagrangian Coherent Structure is that it's perpendicular in every point to the eigenvector K2, which is associated to the maximum strain, so the maximum eigenvalue of the Cauchy-Green strain tensor. And therefore, the strain line, as stated in the slide, is tangent to the other eigenvector, which is K2. So this strain line can be obtained solving the given Cauchy problem, in which the tangent to the strain line is the eigenvector parallel to it. The initial condition is given, and then we can integrate it and identify this one-dimensional object, which is our repelling structure of the flow. In order to assess the ballistic capture phenomenon and be informed by what we call the time-varying finite-time Lyapunov exponent, we introduce a generalization which will allow us to compute the weak stability boundary, which is to consider a time-varying integration, an initial condition varying integration time, which is associated to the number of revolutions performed around the target body. In other terms, the eigenvector of the Cauchy-Green strain tensor is associated to a propagation whose time is the time necessary for the object to perform n revolutions around the target body. In this way, as given in the equation, Tn is a function of s through x of s. And so it's, again, it's a variable integration time. Now it's worth noticing that the stroboscopic strainline is defined in R2, in two-dimensional space, while the physical flow is defined in, operates in R6. So we need to introduce some mappings to deal with a mapping that is defined in R2. We can do that simplifying the phase space we're looking into. And for example, we can fix some of the initial osculating orbital elements of the trajectory. And we can add some reference frame transformations and some projections, such that the resulting flow is a two-dimensional one. In this way, all the formalization of the stroboscopic strain lines makes sense and can be applied to a flow that physically starting is six-dimensional. Here we show this plot in which you can again understand the conceptual steps necessary to compute stroboscopic strain lines. First of all, and I didn't say this before, we restrict our search on a one-dimensional space. We perform a bisection search, a search via bisection method, and we identify a point on the weak stability boundary. That is a point that's unstable on the right and stable on the left. Once we identify that, we can propagate it. Once we intersect the initial semiplane defined by the initial condition, we stop the integration, we obtain the state transition matrix associated to such propagation, we can compute the Cauchy-Green strain tensor, we can perform its second decomposition, obtain the K1 vector, and from there we have performed basically an integration step for the stroboscopic strain line, because then we can perform one integration step for the stroboscopic strain line, go back to integration of the trajectory in six-dimensional space, making again use of all these projections, and obtain the stroboscopic strain line. So, first of all, we start from the results showing the ballistic capture set, in particular the stable set, associated to 1 and 2 revolutions. These are results associated to orbits around Mars, in which we're dealing with both high-fidelity models, in which we're dealing, for example, with the perturbations of Jupiter, Deimos, and the Earth, the Sun, and a number of other perturbations, such as solar radiation pressure and non-spherical gravity of Mars. But also we can deal with more simple dynamical models, in which we just consider the attraction of Mars, the presence of the Sun and the Earth, or even without the Earth. And you can see that here we get these figures that represent the stable set and whose border is the weak stability boundary. We can then use the proposed technique to compute the stability boundary, the weak stability boundary, and obtain the results given in the figures. You can see that the green line, which is the stroboscopic strain line, is matching the outer border of the stable set. That is the weak stability boundary. So we successfully approximated it using this new object. Moreover, we can use the same approach to approximate the border of the x-1 unstable set. And that's what we're doing in this slide, dealing with the high fidelity model. And you can see that, again, the matching is there. The idea is that the x-1 unstable and the w-1 stable cover the majority of the phase space. So if we approximate one, we can approximate the other. So it means that the crash set and the acrobatic set are made of a few initial conditions. So because we can approximate both, we can therefore approximate the capture set by taking the interception of these two sets. And these results are given here for the C1, C2 sets, and again in the slide following this for the C4 and C6. Then we can apply the same technique for the high fidelity model, and we are again having a good matching, particularly for C1 and C2. And then we have the results for C4 and C6. From here we can then look into the region identified by the two stroboscopic strain lines and propagate initial conditions located around the region of the intersection. And it turns out that these trajectories are capture trajectories, which are shown in this slide. Here are for two different cases, for two different model fidelities. And we have trajectories associated to initial conditions in the C6 sets. You can see that the orbit is coming from outside the sphere of influence, and it's performing, after being captured, 6 revolutions around the target body, which is Mars. The same trajectories can therefore be represented in different reference frames. Here we have the inertial reference frame, but we can also relate these trajectories to the three-body problem, which is a natural way of describing the ballistic capture phenomenon, in particular the elliptic one. And you can see the behavior of these trajectories passing around one of the two collinear Lagrangian points and then start orbiting the target body. So in conclusion, the work aims at developing a ballistic capture trajectory design strategy, starting from a characterization of the phenomenon informed by the theory of Lagrangian Coherent Structures. So we went from the variational equations to the Cauchy-Green strain tensor, and then we informed with the Lagrangian Coherent Structure theory stroboscopic strain lines, which have been introduced and have been shown to approximate the weak stability boundary of given problems, both of high fidelity and low fidelity. So as said in the final point, this technique is effective independent of the level of fidelity of the underlying dynamical model onto which the flow-informed strategies are imposed. As recommendations, in addition to what I said before about the computation of the time-varying finite time-Lyapunov exponent for different dynamical systems, it could be interesting to apply the proposed methodology to different two-dimensional subsets of the phase space in order to understand some features of the capture phenomenon. Moreover, it could be interesting to generalize the technique to high-dimensional mappings, so remove all the mappings necessary to go from R6 to R2 and apply directly something to the R6 mapping. And finally, from a theoretical point of view, it could be interesting to investigate whether stroboscopic strain lines identify Lagrangian coherent structures or not. Because practically speaking, we can understand that these structures define a repelling object that separate the motion in some way, but because we are dealing with a time-varying integration time for each point of the stroboscopic strain line, it's not obvious what's the theoretical implication of this. So it could be interesting to look into it. And that's all. I thank you a lot for your time. Here's my email if you are interested in discussing more about this work or other works. And I thank you for your time.